Okay, I started my recording. I'm going to go ahead and start the review and see if anybody else shows up. Just a reminder, this is a review for, not that one, Exam 8. Chapter 16. Let me get my facts together. Here we go. Okay, so we're going to have this review, and then, oh, hold on a second. I got the wrong. How did that happen? Let's try that again. Yeah, I was right the first time. Six, 17. There we go.
Sorry, I'm a little bit late.
You probably already got these two. So you want
I actually forgot to add.
Oh, okay. So grab one each. That's our last lab there on the right. And
Oh, we have 2 more labs.
I don't think so, unless you missed one.
Honestly, can't tell you. It's been.
No, you were there.
Okay.
We did the formation constant.
Yes. Yeah. Never mind. Never mind.
And then the makeup battery is the last one.
Yeah. I've had a week. Well, the past couple of weeks.
Okay, so we're going to review today chapter 17 on entropy. And then the exam will be 2 weeks from today, because next week is Thanksgiving break. So you'll have 2 weeks to get ready for exam 6 on this chapter. And then we'll follow that up on that same day with chapter 18, electrochemistry. The problem there being that we won't have time for a review on electrochemistry. So what I'll do is I'll post a previous review session. I think I recorded it in the spring. And so you can just go to Blackboard and call that one up, and that should help you review for the following week, which will be, unless the exam schedule changes, it'll be on the 9th. It'll probably be the same.
So exam 7 will be on the 9th?
Yeah. Unless I haven't seen an exam schedule yet. I haven't looked that hard either. But if there's a major change, then I'll poll the class and see if it's going to interfere with anything else. I figure as long as it's on Monday, then you guys will be good, because the rest of the week is taken up by MLT, right? So if I can stay out of the way of MLT, we'll be good. Okay, so that's enough housekeeping. Let's get on with the meat of the topic. Entropy. How do we tell reactions are spontaneous? I could try to do a review, but I think it would probably be just as effective to go through the review document and pick out problems that you guys are either having trouble with or just run down the list, and when I find a new topic, we'll just stop there and do one. This review document is version 1. There's a version 2 on Blackboard. You might want to take a glance at that one to see if there are any major differences. I tried to generate the version 1 and version 2 so that they would cover the same topics. But sometimes when you're covering a topic and you actually look at a problem based on that topic, it look completely different than the other one. They have a tendency to do that. Well, are there any problems that are really giving you trouble we need to get to right away?
I say we just jump in.
Okay. So if we look at, we'll just start with number 1, see how far that gets us. So we're looking for which one has a delta S that's negative of these 5 possibilities. So you're going to evaporate 1 mole of carbon tetrachloride. I can see where this one's going. Try this. Well, let's just take a look at it. First of all, what do we mean by delta S being positive or negative? If delta S is by itself, what are we referring to? The system or the surroundings? Right, the convention would be, if there's no subscript, we're talking about the system. So we have to define what the system is, and in many cases, the system's already defined. So when we evaporate 1 mole of carbon tetrachloride liquid, that quantity of carbon tetrachloride is the system. And the surroundings are whatever the carbon tetrachloride goes into. So in this case, what do we mean by positive and negative delta S? Delta S is an expression of change in entropy, right? So if the disorder increases, delta S is going to be positive. So is the disorder increasing for this process? I would say yes. So this delta S is, let me put it over here. This one's positive. Right? So that doesn't satisfy the conditions. What if we mix? It's going to be one of those days. Try red. What if we mix 5 milliliters of ethanol? That's my abbreviation for ethanol. Okay. With 25 mils of water. So the system is our ethanol being dissolved in water, but we focus on the ethanol. So what's happening to the entropy there? When you take the ethanol and put it in water, is it becoming more ordered or less ordered? It's becoming less ordered, right? I mean, less ordered, more disordered. So more disordered is a positive change. Okay. Compressing 1 mole of neon, 1 mole of neon at constant temperature, and the volume goes from 1.5 liters down to 1/2 liter. So what's happening to that neon when we compress it?
More ordered.
More ordered, which means less disordered, and that means yes, that's negative. A negative change in disorder means more ordered. So that would answer the question. For D, raising the temperature of copper from 275 to 295. Copper to from 275 to 295 K. Now, at this point, we're seeing more vibration and movement of the copper atoms as we increase the temperature. Right? So that also translates into an increase in disorder. What it actually means is the copper is entering more possible microstates because of the rapid movement. So that means the delta S is positive. And then the last one is you take a single crystal and grind it. That's more disorder. So the only one that is a negative delta S is C. Okay, that was one. I think two is going to be interesting as well. Two is sort of an approach to understanding microstates. It has to do with probabilities. So if you have two pyramid-shaped die, which is plural? Die is plural of dice, isn't it? Or is dice plural? Die is plural?
No, die is singular.
Singular.
Dice.
Okay, so I got it right. We have two dice. We have two dice, and they have 4 faces. So that means they're tetrahedrons, right? And there's a 1, 2, 3, 4 sequentially on the faces. And we toss them, and which outcome has the highest entropy? Okay, let's try this one. So what are the possible outcomes? Well, you can roll 1 and get 1, 2, 3, and 4 out of it, right? Or you can roll the other one, right? This is die number 1, and this is die number 2. And you can get 1, 2, 3, 4 out of that one. So what are the possible combinations? Well, you can look at it several ways. I mean, you can write 1-1, but we're going to do it as summations. So this has a sum of 2, 3. That's going to be hard to see on the recording. I need to get something that's darker. 4, 5. So that's the summation of those. This one has 3, 4, 5, 6. And this one has 4, 5, 6, 7. And this one has 5, 6, 7, and 8. Right? So which one has the highest entropy? The one that occurs most often. Right? That's the highest entropy. The largest number of microstates. We've only got one with 2 and one with 8. We've got 2 with 7, 2 with 3. We've got 3 of 4s and 3 of 6s, but we've got 4 of that one. That's the highest microstate, where the sum is and that's C, where the sum is 5. So the whole point of that question and the answer of it is just to emphasize the probabilistic nature of a discussion of entropy, which is the most probable state. And that's where the summation is 5. So wherever you have, say, 4 together with 1 or 3 together with 2, that's your most probable state. Okay. Let's see, we can skip 3, I think that one's very simple. 4 is another situation. Right? In 4, we're actually looking for the ones that have positive delta S. How many of them have positive delta S? 3 of them do. The other one's negative. So what about 5? Is that a topic we need to deal with? Could be. Let's see what we can learn from 5. We'll have to smash the tip on this one just to get it to work. Which of the following statements is true? Total energy and entropy of the universe are both increasing. So energy is increasing. Let me see, how do we express that? Change in entropy is greater than 0. And change in energy and entropy are both greater than 0. So they're on the rise. Total energy is increasing, but the entropy is constant. And this is of the universe. Okay, all these statements are for the universe. And when the author of this problem says universe, they actually mean the universe, everything. We're still, for C, we have increasing entropy and increasing energy, and entropy is decreasing. And the last one, well, the next to the last one, energy is constant and entropy is increasing. And then E is none. Okay. So the approach to this one is, what do the laws say? Right. So what does the first law of thermodynamics say? Energy in the universe is constant. It can move from one place to the other, but the total amount of energy is change in energy is 0. That makes this one. So with the selections we have, well, actually we could say that one's it, because that's the only one that has this. Trouble is, we got this one. Yeah, so we do have to see if that's true. Change in entropy. Is it on the rise? In the universe, yes. This means that the universe is gradually, but constantly, well, not constantly, it's eventually going to reach maximum entropy. There's so much disorder that you can't extract any more energy out of it. So this one is true also. This is the first law of thermodynamics. That's the second one. Now, this one's true here, but that one's not true. So this is the only one that's true. Okay, simply based upon the laws. Oh man, this is not good. Well, it is what it is. My video part was up in a little inset. Julianne was the big box. So hopefully, I don't know. We'll have to see what comes out of that. Okay. So that was 5. So let's go ahead to 6. This is nerve-wracking. So for 6, a chemical reaction is most likely to be spontaneous. Under what conditions? Two things drive a reaction. The amount of energy in the products is lower than the amount of energy in the reactants, right? So a change in energy of the system in which you have less energy for the outcome, right? So it's a negative number. That tends to be spontaneous. But not just that. The other thing that tends to be spontaneous is if the entropy of the system is actually increasing. Now notice we're talking about the system now, not the whole universe, right? So it's possible to have decreases in entropy or increases in entropy and energy also, positive or negative. With a system, as long as it's coupled to surroundings, which go the opposite direction. So if you couple a reaction to surroundings where the entropy is massively increasing, then you can decrease the entropy of your system and it'll still be spontaneous. Okay. But in general, if the energy of the products is less than the energy of the reactants, and the change in entropy is positive for your system, then that reaction tends to be spontaneous. And that would be B. Okay. I'm just going to have to keep switching these off until one gets light, and then I just go to the next one. This one. Guess I'll try that one. Okay. How about 7? So let's see, what are we given for 7? The heat of vaporization for 1 mole of water at 100 degrees and 1 atmosphere is a value. So we're going, the vaporization of water, we're going from liquid to gas. And the heat of vaporization is 40.56 kilojoules per mole. And that's a positive value. So we're putting energy into the system in order to get that to happen. And this happens at 100 degrees C and 1 atmosphere. So let's stop for just a second. What is this? This is a phase change. And a phase change is a point of equilibrium. Remember that diagram that went like this? Right? You heat the water up, well, ice. You heat the ice up, right? You can add energy into it, but when you get to the phase change, the energy level stops, levels off until all of it's gone. We're in this equilibrium phase, whether it's going from ice to liquid or liquid to gas. Okay? So under those circumstances, we're at equilibrium. And the question is, what is delta S for that process? So that's for the system. All right, so if we look at it purely in terms of entropy, we know that the S, what did I say? Didn't say total. Right, the authors like to use universe, but you can get the universe easily confused with the whole universe or an isolated system. Right? So we're an isolated system here, system and surroundings. So that is equal to change in the system plus the change in the surroundings. And when we're at a phase change, an equilibrium situation, in this case, it's equilibrium phase change, but the same holds true for equilibrium in a chemical reaction. So if you reach equilibrium in a chemical reaction, this is also true. Those two together, summed together, are equal to 0. Okay, so next step. How do we calculate? We have a formula for calculating this one. Delta S of surroundings equals what? Negative delta H divided by temperature in K. So delta H is 40.56 divided by 100 degrees, which is 373, right? K. And that's a negative. So I don't have to pull out my calculator. This would be a negative 109. Well, that's kilojoules. Okay, so kilojoules would be 40,560 joules divided by 373. Now, why did I do that? Because most often entropy values are reported in joules, not kilojoules. Because the change in entropy is usually 3 orders of magnitude less than the heat changes or energy changes. So now that becomes negative 109 joules per K, actually K mole. Now that's delta S of surroundings, right? But we know at equilibrium, these two have to add up to 0. So that means the system had to change exactly the same amount, only with opposite sign. So that's why the answer is a positive 109. In other words, the system here, entropy increased from liquid to gas by this amount. Okay. I thought I pinned that. Pin video. There we go.
Can you hear me?
Oh, is this Megan?
Yeah.
Okay. I just see iPhone. I don't see you.
It's me.
Can you prove that? Okay. Everybody's here, technically speaking. All right. So we're up to problem 7. And let's see. I'm trying to go down the list and just pick out things that are different. Let's see. Keep myself on track here. All right, so actually a corollary to this one is number 8. So I'm going to leave that one up there for now. So number 8 says delta S of surroundings is favorable, unfavorable for exothermic reactions and favorable, unfavorable for endothermic reactions. So first of all, what are we given? Well, we're given 2 situations, exothermic and endothermic. Okay, so we know that the delta H for exothermic is going to be negative, and the delta H for endothermic is going to be positive. And the question has to do with what's the delta S of surroundings. So we know from this relationship here, negative delta H divided by T, we can approximate what the delta S is going to be for these. Now, this is not absolute because we're only talking about entropy here, and there are other factors involved. But the delta S of the surroundings then would tend to be, well, what do we mean by favorable? That's the question. Delta S of surroundings would be favorable if the delta S of the system increases, then the delta S of the surroundings would have to decrease. So how would the delta S decrease? This would have to be negative, if my logic is on track. Well, no, my logic isn't on track. The idea is for the delta S to be positive for surroundings. So I think that's a bad question. I'm going to try to reason out the answer, but it's not something that I'd want to hit you with on a test because it's really, it defies logic. You know, if we're trying to get the system to go for more entropy, then this is going to backfire. Exothermic would be negative, so that means for this one, delta S would be positive, and that's surroundings. Okay. And for this one, endothermic, the delta S would be negative. So we're saying that favorable, unfavorable, which leads us to favorable, unfavorable, A. In actuality, it depends on whether or not this is an equilibrium situation or not. If it's an equilibrium situation, then if one gets positive, the other is going to be negative, like it did here. But if it's not equilibrium, then we have to know what this is. And the information here is incomplete. We would need to also know what is the change in energy. Right, so we could calculate free energy. Right, so that's really not a good question. But I gave you the answer and the reasoning anyway, so in case I slip up and it shows up on an exam, then you'll know what to answer. Or if you see it on a standardized test. Because all these questions that I'm using have been vetted by real chemists. So that's what they're expecting. All right. So let's see. I want to get something that's, let's see. Okay. Sorry for the dead air. $12 is kind of a trick question. And we really won't have to go in there and dig at it. It says substance X has a heat of vaporization of some value. So the heat of vaporization is some value at its boiling point. That's the key. If it's at its boiling point, then the delta S total is equal to 0, which is delta S surroundings plus delta S system. Right? So at the boiling point or at the melting point or any other equilibrium situation, the total is always 0. So that means that this one has to be the same as that one, only the opposite sign. Right? So back to 12. The value of delta S for the universe, and when we say universe here, we mean total. So the universe, the delta S is 0. So it's kind of a trick question. Not kind of, it was. Let's see. It looks like I got a repeated one down here. Delta S is favorable for exothermic, and you know what? Where was that? 8. The only difference between 8 and 14 is that 8 has delta S for surroundings, and 14 has delta S, which you can take it to mean delta S for the system. And for 14, we're saying that the delta S is insufficient. I mean, there's not enough information. You can't tell. Now, why can't you tell? Well, the explanation is for 14 that the only way you could tell whether it was favorable or unfavorable is if you were at equilibrium. If you're at equilibrium, then the delta S the delta S for surroundings would be the opposite sign of the delta S for system. So ideally, if we were told that we were at equilibrium, then we would get we would be able to say that this is the opposite of the number 8 answer. It wouldn't be the opposite. Actually, it would be the same. So that's not a good one either. Let's stop wasting my time on these bad questions. Let's find some that will actually take us someplace. Let's see. Okay. What about 17? Which of the following statements is always true for a spontaneous process? Okay, so we have a spontaneous process. And what do we know about a spontaneous process? Well, two things. Either we know that the total change is positive, right? So the summation of the system and surroundings, if put together, we get a delta S total, and that's for an isolated system, is positive, then it's spontaneous. Or if we're able to calculate delta G is negative. If delta G is negative, free energy is negative, then we can also say that the process is spontaneous. So let's see, what are our options? And I think we have 4. Okay. So delta S for the system greater than 0. Delta S for the surroundings greater than 0. Delta S for the universe or total is greater than 0. And the delta G for the system is greater than 0. Always true for spontaneous. Always true. All right. This is never true for spontaneous. Delta G has to be less than 0. So that can't be true. This one, greater than 0. Yes. If that's just the second law of thermodynamics. And we're applying it in specific situation where we have an isolated system. If delta S total is greater than 0, we have a spontaneous situation. For these two, one could be by themselves, you can't tell. Right? So sometimes this could be negative and that could be positive. This could be positive and that could be negative. It's the summation of the two that gives you this one greater than 0. That tells you spontaneity. So these two by themselves will not always be true for spontaneous reaction. This is the only one that's true for the spontaneous reaction. or spontaneous process? Right, that's why the answer is B. That's a good question. Finally got one. That holds true for the laws, the principles that we're given. So when I say a question is bad, it's not necessarily false. It's just, it doesn't seem to follow well from principles. That's what I'm talking about. So we finally found one. How about, let's see, what do I want to do next? Let's see. '18 refers to, okay. Yeah, 18 might be a good one. If I've got enough blue left in my marker, doesn't appear to be. So let's try a red again, see if it's had a rest. Okay, there's 18. And for a particular chemical reaction, delta H is equal to negative delta positive 4.3 kilojoules. And delta S is equal to negative 19 joules per K. Under what temperature conditions is the reaction spontaneous? Okay, how do we tell spontaneous when we have these two values? You go to Gibbs Law or Gibbs formula. Delta G equals delta H minus T delta S. Now we're looking for spontaneity, we're looking for a negative delta G. Okay? Right, so under what conditions would this be spontaneous? Well, if delta H is negative and delta S is positive, all temperatures, right? Any temperature times this will give you a negative number plus a negative makes a negative, okay? If this is negative and this is negative, what will give you a negative combination? You want to make this term as small as possible because a negative times a negative is a positive. So this is very low temperature. Okay? If this is positive and this is negative, then you want to make this term, no, under those conditions, no temperature. That's never spontaneous. Why? Because this is positive and a negative times a negative is positive. Doesn't matter the temperature, it's always not spontaneous. The other possibility is both positive, right? So if they're both positive, then you want to make this term as large as possible to overcome that positive. So for this one, high temperature. Okay, that's just a review of conditions that favor a reaction. So spontaneous, this one's never. And these, this one's always, and these are conditional. Right, so now we can look at our selections. We want to find out C, D, and E. So under what conditions? When T is less than negative 226, or T is less than positive 226. So that's a low T and this is a high T. Reaction is spontaneous at all temperatures. or the reaction is not spontaneous. Not spontaneous for any T. And then E is T greater than 226K. Okay, so let's look at this one in terms of what we know over here. Positive here, negative here. Positive here, negative here. What does that mean? That means doesn't matter, doesn't matter, never spontaneous, doesn't matter. It's not spontaneous at any temperature. Okay, simply because that's positive, that's negative, and the condition here say it's never spontaneous. Now, when would that reaction be spontaneous? That's kind of weird. I just said it's not spontaneous. What would make it spontaneous? Any ideas? Yeah.
I was gonna say that was my
Oh, that was your phone. Okay. If a reaction is not spontaneous this direction, it's always spontaneous that direction. Okay. So you just run the reaction in reverse if you want the spontaneous version. Okay? Or did that twist your head around?
Kind of makes sense if you want the opposite reaction, just go back.
Right. That would make this one negative and that one positive. So negative and positive, all temperatures. It would be spontaneous if you run it in reverse.
Right.
Okay. I think we milked that one for all it's worth. Okay. 18. And let's see. Yeah, that's not a good question. Let's see if we can find a better one. Okay. This requires some calculation, number 20. All I have to do is squeeze some action out of these dry erasers. That one's not going to do it. Get rid of that one. Let's try green. Haven't used green yet, have I? That's 20. Okay, so we have a reaction of A plus B yields C plus D, and delta H is equal to plus 40 kilojoules, and delta S is equal to plus 50 joules per K. So the selections that we have are conditions under which it's spontaneous, right? So spontaneous at T less than 10K, right? Spontaneous for these selections, T greater than 800K, only T is between less than 800 or greater than 10K, and all temperatures. So that's your reaction is favorable for cheater detergent. All temperature, bad joke. Or never spontaneous. Okay, so let's look at, since we have delta H and delta S, we can plug that in and find out what the delta G is and speculate on the temperatures. So the delta H is going to be 40 kilojoules. So we have to match our units. That's one thing you've got to be careful about. This is kilojoules, that's joules. So I usually change the kilojoules to joules. So that's 40,000 joules for delta H, positive. And then a negative 50 joules per K times the temperature. Okay, so if we want this one to be, if delta G needs to be negative, I would say set G equal to 0. Find out what your T is, and then compare that to what would make it negative with that T. Would we have to go up with the T or down with the T to make this negative? So if we set this one equal to 0, and we say 40,000 minus 50T, then we put the 50T on this side. Right, before we can divide, we gotta get that over there. So T equals 40,000 divided by 50. Right, so 5 into 4,000 would be 800. Okay. So that's for delta G equals 0. What would make delta G negative? Well, let's look. If this were 800, that would make it 0. So how could we make it less? Right, make it negative. We would have to make this whole term negative, wouldn't we? And we'd have to make it larger than this one. 800 times that is exactly 40,000. So if you make 800 bigger, T greater than 800, then we would make this term more negative and drive this one to negative. So it'd have to be 800, temperature greater than 800 here. Like that. So if I got that right, it should be B greater than 800. Now, is it obvious how I work that problem? Maybe not, unless you've worked a few of them. Right? But if we want to find out what temperature is the turning point from positive to negative delta G, you set it to 0 first. And then you find out where your middle point is and then which way you need to go. That's the logic. Okay, that was 20. All right, let's see. Oh, that's 22. Okay, let's do 22. This takes a little bit more effort. We have to break it down into pieces. All right, so we're given this reaction, already balanced for us. Okay, and the delta H for that reaction is 789 kilojoules per mole. So the question is, what is delta S total? It says universe, but we're actually talking about total. So how do we get that one? Well, we need delta S for surroundings, right? Plus delta S for the system. All right. We're not told that this is equilibrium. In fact, it's definitely not equilibrium, because we would start off with solid iron, iron metal, oxygen, water, and make iron-free hydroxide. Right, so it's not equilibrium. That means we cannot assume that delta S is 0. We're going to have to find out this term and that term before we can find out this one, because the question asks, what is that one? All right, so how do we do that? 22. For the system, we know that, and this is 25 degrees, this is important. 25 degrees C, 1 atmosphere. Right, so that means these are standard conditions. All right, so now that we know that they're standard conditions, we can find out what the delta S for the system is by adding the delta S's, by adding this delta S to itself, then subtracting the delta S for these. Right? So the delta S for system is going to equal that one, 2 times whatever that is. And we look at the chart, we have 107 joule per K. And then we subtract the delta S for these. So the first one is going to be, and remember, for delta S's, you always have a value, right? For delta H's, the value for this would be 0, right? Because it's in standard state. But for delta S's, every term has a real value. They're never 0. So iron is going to be 27, right? And then we're going to add 3 halves for oxygen, which is 205. And then for water, 3 times water, which is 70. Right? So now that one gives us, if I did that right, yeah, that one gives us a negative 357.5 joules per K mole. That's for the system. Okay? How do we get the surroundings? Remember those earlier problems we did? This value is equal to negative delta H divided by T. Okay? So we know what the delta H is, minus 789 kilojoules. Kilojoules. So how many joules is that? Negative 789,000 joules per K, divided by the temperature, K. So 25 degrees and K is what? 273, so 298, I think. K. So what would that be? (2648) joules per k-mole. Okay? Now, add those together. Right? Add this term, because it's here, this term, because it's there, and we get what? Well, that's not exactly right. Better do that calculation over. 375.5 negative, and then 2648. Is this one right? 300 times 2500. Yeah, that's right. And we'll add those together. So that's 2.27 times 10 to the third. 2.27 10 to the third joule per k mole. All right. Oh, I see. I made a mistake in my worked problems. I left out the K. I better fix that. You see where I made the mistake? In the worked problems, number 22. My answer, 2270. Well, this is 2290 joules per k mole. And since the answers are in terms of kilojoules per mole K, I had to convert this to kilo right here. So that's why 2.27, or that answer is 2.29. It's some kind of rounding error. Kilojoules per k mole. Right. So is this reaction spontaneous? Yep. Because the total is positive. It's very spontaneous. Okay. How are we doing on time?
2:15.
When does lab start? Not that we have lab, but I'm just thinking about when I'm digging into lab time.
I think it's like right around
4 o'clock. Yeah. Okay, so we're good. We're still in lecture time. Okay, that was 22. Let's see. $23 is really a simple calculation. I don't even know if it's worth doing. Might as well. Somebody might be interested. So the following reaction, water converted to gas, steam that is, has a delta H of positive 44 kilojoules per mole, right? So it's endothermic. And a delta S, and because that has no subscript, that means delta S for the system, is 0.119 kilojoules per mole K. Okay, so whoever did this was kind enough to convert this to kilojoules for us. So when we put them together, we don't have to worry about the units. So what's the question? Which of the following must be true? All right. A, not spontaneous. B, spontaneous. C, delta G equals 0. D, delta G less than 0. Or E, 2 of the above. Okay. So under what circumstances would 2 of the above be true? Spontaneous and delta G less than 0. Right? So if these are true, if it's spontaneous because delta G is less than 0, then E is the answer. Delta G would only be equal to 0 if it wouldn't be spontaneous, it wouldn't be non-spontaneous, it'd be just is. And then not spontaneous would be delta G greater than 0. So looking at the answers, that tells me that the best approach is to find out what delta G is, right? So delta G is delta H minus T delta S. So delta H is 40 kilojoules per mole minus temperature. All right, what's the temperature? Do we know? Yes, I missed that part. 120 degrees. So we do want to know what the temperature is. 120 plus 273. And then times delta S, 0.119 kilojoules per mole. Okay. So what do we get out of that? I'm going to calculate this one just to be sure. I didn't make another mistake. So 120 plus 273 is the temperature. So that's 393 here. Okay, times 0.119. All right. So this term is 46.77 kilojoules per mole. And this one's 40 kilojoules per mole. So we subtract this one from that one, and we get a negative G. We get negative 6.77 kilojoules per mole is delta G. So delta G is less than 0 here. And that means it's spontaneous. That's why E is the answer. Okay. Let's see what else we can do. Ooh, 24 looks interesting. For which of the following processes would delta S be expected to be most positive? So we want the largest delta S, and that makes it system. Right? So we've got oxygen, gas, plus 2 hydrogens, gas, yields 2 waters, gas. Okay? And the state is very important, especially when you're talking about entropy. So we go from water liquid to water solid. All right. And this one is ammonia gas plus hydrogen chloride gas yields ammonium chloride gas. Okay. This one is 2 ammonium nitrates solid yields 2 nitrogens plus an oxygen gas plus 4 waters gas. And this one goes from N2O4 gas to 2NO2 gas. All right. 2 things to consider here. If we're looking for the largest change in entropy, we want to look for one of 2 things, actually both, if they're available. Are we making a phase change? Are we going from a solid to a liquid, or a solid to a gas, or a liquid to a gas? That would increase entropy. The other is, if you're just looking at gases, then an increase in entropy would be, if you start with so many moles on the reactant side and you have more moles on the product side, that also is an increase in entropy. So let's look at the ones and see if we can eliminate any. Are there any with negative delta S's? Liquid to solid, that's out. How about, that's it. Okay, so now we've got gas to gas, gas to gas, solid to gas, gas to gas. Okay, what's the change here? 1 mole to 2 moles. So this is a positive delta S, that's true. 1, 2 to 1. That's going from 2 moles of gas to 1 mole of gas. That's a negative delta S. So that one's out. How about this one? We're going from 1, 2, 3 to 2. That's a negative, right? So it's not positive. So it's a toss-up between D and E. This one's a positive. This one's going from solids to gases. So that's definitely a positive. Which one's the biggest positive, though? Well, we're going from no gas to 7 moles of gas in this one. In this one, we're going from 1 to 2. So it should be fairly obvious. Not only are we changing phase, but we're getting 7 moles of gas here versus 2 there. So this is the one that has the largest positive delta S. Okay? Okay. Let me see. Let's look at, okay, we've done one like that before. Done one like that. 29. That could be a sticky point. And I put in, let's see, I don't know. Maybe. That's not it. Page 7. I did put it. Okay, so I put that red comment on page 7 at the bottom to try to help you deduce for 29 which of these are not state functions. Right, so what's a state function? State means present. What is it right now? Doesn't matter how it got there. Right? Whereas path is dependent on how you arrive. Right? So, which ones of these, let me put them up there. Q, it's A, B, G, H, E, and P. All right, so ask yourself, which one of these depends on how it got there? What is P? Pressure. Oh, pressure, of course. Does it matter how we get to pressure? No, it just is. It's a value. So that's state. How about energy? The amount of energy in the system, internal energy, you measure it right now. You don't care how you got there. How about enthalpy? That's a state function. Enthalpy refers to potential. Remember when I discussed the difference between Q and H? H is a state function because it refers more to potential for the system. So that's a state function. And free energy, that's a state function. The only one of this group that's a path function is Q. Now, if pressure is constant, then Q and H are the same. But still, if other factors change, then the Q will also change. Now, what path function have I left out of this one? Or the question? The question left one out. W. Work is a path function. Okay? So I guess those are the only terms that I can think of. Well, we can think of T and V, ET, moles. These are all states. Really, the only path functions that we've studied so far are Q and W. But we also said that change in internal energy is what? Q plus W. Right. So this may be a state function, but it also results from the summation of paths, which means this one is stable. It sits there at its state, but how we get there determines what this value is. So if we put these two together, then the internal energy can be determined. But after we've added those two together, it doesn't matter how we got there. Okay, that was 29. Let's see. Get something different. Okay. This one looks promising. About 31. Is that visible? Oh, that's awful faint. Need something darker. That's better. I gotta remember not to use green. Okay, given the following data for enthalpy of fusion and standard entropies. Okay, so N2O4 has a standard enthalpy of fusion of minus 20 kilojoules per mole, and standard entropy of 209 joules per K mole. Okay, and that's the liquid. The gas has a standard enthalpy of formation of 10 kilojoules per mole and a standard entropy of 304.2 joules per K mole. Okay. The question is, greater than what temperature in degrees C is the vaporization of N2O4 liquid spontaneous? So under what conditions is this spontaneous? Okay, we want to know spontaneous temperature. All right. So we need to know a couple of things. First of all, how are we going to find out this temperature? Well, what formulas do we have with temperature in them, right? Delta G equals delta H minus T delta S, right? But I don't see any delta G's in there or even how to get delta G's out of that. So we can't use that one. What's another one we know? That one. Okay. So if we could find out, we have delta S's in here. Those standard delta S's are for the system, right? This is an equilibrium process where you're vaporizing a liquid. So we know that under those circumstances, the system would then be the positive of this one, right? Because add them together and you get the, add these together, you get 0, which is total, right? So that's key to understanding how to do this one. This one is an equilibrium process. We're at a phase change. So we can say that this one is the positive of that one because added together you get 0. Okay, so that's good because now we know that all we have to do is find out what this one is, delta H. And the delta S for the system here, we can deduce from this one minus that one, right? So delta S for the system is going to be this one minus this one, joules per kmol, which is what? Sometimes I can do these in my head, and sometimes I can't. Depends on the time of day, phase of the moon. Okay, so I've got 95.2 joule per k mole is delta S for the system, right? So how do we find out what delta H is? Well, the delta H for this one is the formation for that one minus the formation for this one, isn't it? So this one is 10 kilojoules per mole minus a minus 20 kilojoules per mole. So that's 30 kilojoules per mole. So that's delta H. But we have to match the units, right? This one's kilojoules, that one's joules. So if we say this one is right here is 95.2 joules per kmol, then this one is 30,000 joules per mole. 30,000 joules, oops, okay, joules. Yeah. Joules per mole divided by T. Okay? So now we just solve for T. Bring T over here and bring that one over there. And that's 30,000 divided by 95.2. And I get 315, close enough, K. But the temperature they want is what temperature greater than T will make this spontaneous. So we just subtract 273. And we get 42 degrees C. So any temperature greater than 42 degrees C should make that reaction spontaneous. Okay? Several steps involved. The key to this one is looking for a formula that will give you temperature for which you have the information. Right? We didn't have the information for that one, but we did have the one for this one. Once you recognize that this one is just the change of sign, and that's only possible because this is an equilibrium situation. We're at the boiling point. At the boiling point, at the melting point, you're an equilibrium situation where delta S total is equal to 0. Okay, that's 31. Let's see, did that show up? Yeah, sort of. I hope it's not going in and out of focus. That's my biggest problem right now. So if I step to the side, looks like it's okay. Weird. Maybe the camera's going bad. You ever had a 4K webcam go bad on you?
I don't normally use webcams.
Oh, okay. I'm kind of ignorant there too.
I'd say about the only time I use webcam is when I can't make the class.
Yeah. Okay, so that one was 31. Let's see. 32 or 3 introduces the equilibrium constant. Let's just go to 32. Now we've got another formula that will help us relate equilibrium constants to delta G's. 32, is it? Yeah, 32. Okay. What's the equilibrium constant for this reaction? N2, gas. Oh, Haber-Bosch process. Who would have thought? 2NH3. And what we want to know is what's K for that reaction. We're given delta G for ammonia. Let's see. How do I do this? Yeah, okay. NH3, delta G of formation for NH3 is negative 16.668 kilojoules per mole. And the reaction temperature is 298 K. Okay. So let's see, do we have all the information we need? Well, remember, delta S is the only value that is going to be non-zero for everything in your equation. Delta H's and delta G's have a 0, and that's for when the component is in its standard state. So 298 is 25 degrees C, right? That's standard. And does it say 1 atmosphere, or do we have to assume that? We have to assume 1 atmosphere. So what's the delta G for this one? 0, 0. Delta G for this one, negative 16.668 kilojoules, right? So how do we calculate the delta G for this reaction? Well, what does the standard delta G of formation mean? We know what the delta H heat, the enthalpy of formation means. It's when this is equal to 1 mole of that, right? So we would write it like this. Actually, that's backwards, excuse me. And we would have standard state here, standard state there. And then to have 3 of these, we need 3 halves. And to have 1 of those, we have 1 half. Right? So this value is similar to the delta H, delta G, standard formation, but we've got 2 of them, right? So the delta G for this reaction is products minus reactants, right? These are going to be 0. So we just say 2 of these minus 0 minus 0, okay? So that's why the delta G 0 for this reaction is twice what that is. That's 16, 112, 13, 112, 13, 13, 3, right? Is that right? 33,336. Let's see. Yeah. And this is kilojoules. Okay. So what is this equal to? In terms of K, it's minus RT times the natural log of K. Okay? So what's R? Well, it's that other one. 314 joules per mole K. Okay. And this is kilojoules, joules. Oh, that was 16 there. Let me check this out. 16 kilojoules. So that's 16 kilojoules, 33. But this, we need, since that's in joules, this needs to be in joules. So I'm going to convert it to scientific notation. 10 to the 4th joules per mole. And then temperature, 298 times K, or KEQ. So we don't get the two Ks mixed up. So now all you have to do is solve. The trick here is to be sure that your units are right. Right? Otherwise, the math is going to give you a wrong answer. So all we have to do to solve for this one is just to bring this one over here, divide, bring this one over here, divide, and that was a negative. So if we say 3.336 exponent 4, and then 8.314, change sign, divide, and then 298, divide. So KEQ equals minus 13.5, thereabouts. Actually, we got more significant figures than that, don't we? We got 4, actually. 13.46. There we go. So is that the right answer? No. What did I do wrong? Oh, this is a negative. So it's positive. But that didn't fix it. Let me try that again. 3.336 exponent 4, 8.314, and 298. All right. So what did I do wrong? That one. Oh, duh. I'm so stupid. Natural log. Okay. So we need to take the anti-log of 1346. So that means e to x. There. .042 times 10 to the 5th. Close enough. is 6.97, 7.042. Rounding error. I think I used 5 significant figures. Yeah, 455. So if you take 455 here instead of that one, you should get the one that's 53, 32. A. Okay. Um, 33 is a little more straightforward. It's actually going from the K value to find out what delta G is for that weak acid. Okay. So for 33, you would have, instead of this with that unknown, you would have this known, and this would be your unknown. So it would actually be easier to solve. All right. That's why we're not going to do that one. Because it's just beating the horse on the other side. Let's see if we can find something that's a little more interesting. Oh, okay. I don't think we talked about this one in class. 34. It's a version let's see. Well, the reference I give to the textbook here is for an older version, so it may not match up with your textbook. That one's crapping out on me. Try this one. Okay. So what is the question? For this reaction, delta H equals 803 kilojoules. Which of the following will increase K? Decrease the number of moles, increase the volume of the system, increase the temperature, all of the above. So the approach I took for this one, let's look at K first. So K would be CH4 and then O2 squared and then CO2 and then water squared. All right. So what are our choices again? Hold on a second. A, decrease the number of moles of methane. Oh, what's the question? Which will increase K? Increase K. Which one of these will increase K? Does changing the number of moles of anything modify K? No. Because if you change the moles of one, he says it's going to shift until the equilibrium is reestablished. So that won't change K at all. increase the volume of the system. Volume increase. That won't change it either. That's another disturbance that Le Chatelier takes care of. The K is still the same. Increase the temperature. Aha. Increase temperature. Okay. Increasing the temperature will change the K. But then the question is, will increasing the temperature increase K? Okay. So all of the above, none of the above, don't matter. We found the one here. Well, none of the above could be it. It just depends. D is wrong. E, maybe. Because if we increase the temperature and the K goes down, then we have E, none of the above. But if we increase the temperature and the K goes up, so we need some way to tell which way the K goes for 34. All right. This is the linear equation for a relationship of K to the various factors. Delta H. Okay, so there's Y equals M, and there's your X plus B. Okay, so when we draw this one out, X is going to be 1 over T, and Y is going to be log of K. Okay. So, and the slope is negative. Negative delta H over R. Okay. Is that right? Yeah, because this is positive. So that positive value goes in here, and the negative slope makes it that. Okay, so that's right. If that were negative, and we put it in this term, that would make the slope go the other way. See that? Right. So this is an endothermic reaction, which makes the slope this way. Now, if we increase the temperature, does it increase K? So if we make this one bigger, make this bigger, this part bigger, it makes this one smaller, right? So increasing the temperature goes back this way. So going back this way puts it up here instead of down here, which increases log K, which increases K. Okay? So that one's true, based on that relationship. Okay, 34, coming up on 3 o'clock. Let me look for other potential sticking points. That's nothing new. About 38. These logic questions tend to give students trouble. And even instructors trouble too sometimes. Especially when you're trying to figure out what the creator of the question was after. Almost like they're taking some kind of illegal drug. They may come with some of these questions. Let me try red again. So which one was that? 38. Okay. Which of the following statements is false? All right. So since we've got answers for A, B, C, D, and E, and there's none of that tricky stuff like none of the above or one of the above or two of the above, we know that if we find one that's false, we can stop. So A says increasing the temperature of the system increases entropy. So increasing temperature yields increasing entropy, or delta S for the system greater than 0. Is that true? Yes. You increase the temperature, you increase the average kinetic energy of the molecules in the system. That means it gives them more microstates. So that was true. B, 2 moles of gas at 1 atmosphere pressure has a greater entropy than 2 moles of gas at 1,000 millimeters of pressure. 2 moles of gas at 1 atmosphere has a greater entropy, than 2 moles of gas at 1,000 millimeters of mercury. Is that true? Well, we've got 2 different pressures here. We got the same number of moles, right? So let's look at this one. Is this one greater than 1 atmosphere? Yeah, greater than 1 atmosphere. So this one has greater pressure. Greater pressure for this one, which means what? Lesser volume, right, according to Boyle. So lesser volume for this one. 2 moles of gas at 1 atmosphere pressure has a greater entropy than. Yeah, we're decreasing the entropy here because we're decreasing the volume for this one. So decreasing volume means less entropy. So that one's true. How about C? The reaction of O3 gas to produce O2 gas has a negative entropy. How do we know? Well, they're both gases, but that equation is not balanced, right? So how would we balance it? Cross multiply, 2 here, 3 there, so that means 6 oxygen, 6 oxygen. So that's a balanced equation. Now we can answer the question. Negative entropy change. We're going from 2 moles of gas to 3 moles of gas. That's a positive entropy change. You have more moles of gas in the same space, which means greater entropy. So this one is false. And that's where you can stop. Let's see. Is it worth going to D? Well, in order to answer D, okay, we could answer D. The delta S for methane is less, for the standard enthalpy for methane is less than that for ethane. So the approach to this one is, how do you form those? Right. So what's the standard formation for these. We need carbon and hydrogen. And for this one, we need, that's the way I did it. Yeah. And for this one, we need carbon and hydrogen. Okay, so we need one carbon, that's good. We need two there. So we're going to gas here, gas here. So we need two carbons here. And we need 6 here. So we're going from 2 moles of gas in a solid to a gas. Kind of hard to tell what the entropy change is for this one. This one's 2 moles of solid and 3 moles of gas going to 1. So the statement is the delta S for methane is less than that of ethane. So we're saying that the standard delta S for this one is less than the standard delta S for that one. Now, I think what I did was I looked up the values and found that the value for the first one, going from 3 moles to 1 mole versus 5 moles to 1 mole, gives us a lower entropy change from 3 to 1 versus 5 to 1. So that's the logic here. And I just backed it up by looking up the entropy values. But the logic is that you're going from 3 moles to 1, which is a decrease in entropy. But the decrease in entropy from 5 to 1 is much greater than it is for this one. So this one's less than that one. That's true. So that's true. True. And how about E? A substance can only have 0 entropy at absolute 0 in a perfect crystal. Is that true? When is the standard entropy equal to 0? Perfect crystal. And which law of thermodynamics is this one? Number 3. Third law of thermodynamics. The entropy of a perfect crystal at 0 K gives you 0 entropy. Okay, that's 38. Now, I better look ahead and see, be sure I'm not missing something. I don't want to do a review that's incomplete. So let's look ahead and see if we can find anything that needs to be hammered. $42. This is kind of a trick question, actually. Let's see if blue will work. For this reaction, X plus Y yields A plus B. Delta G is equal to minus 1324 kilojoules. So A says the reaction is thermodynamically favorable. Is that true? That's a negative. It's true. Reaction is spontaneous as written. That's another way of saying favorable. Spontaneous, true. The products are more stable than the reactants. Products more stable. If a reaction is spontaneous, that is a major assumption, that the reactants are more stable than the products. That's why they want to go that way. So that was true. D, the reaction will proceed rapidly from left to right. Rate fast, as written. Is that true? There's no way to tell. Thermodynamics has absolutely nothing to do with kinetics. They're two different topics. Thermodynamics says, yeah, the reaction is spontaneous, or no, it's not. But it doesn't say how long it's going to take to get there. And I think the example I used in class was diamond. Diamond is thermodynamically unstable. It will degrade or oxidize in the air eventually. They just take it thousands and thousands and thousands of years to get there. Right? So this one's false because it says something about kinetics and thermodynamics does not. Three of these statements are valid. Ooh. That one's true. Oh, but we were asking which one was false, right? So true, 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 false. Okay. Let's see if I can find something else in here. Let's see. Oh, hold on a second. Let me see here. I don't think this one was in here. No. Let's do this one. It doesn't have a number. Let's see if I can do it before I completely run out of color. Say you're given this diagram of this graph here. This is 1 over t. Here's the origin. This is 0.1. This is 0.2. And this is log k. We have 1, 2, 3, 5. Okay. And the there's the curve for our reaction. So the K is related to T by this equation. Okay. What's the delta S for the reaction? That's the question. Delta S for the reaction equals what? This is a case of interpreting the graph and knowing what each of these means. All right, so this is the X term, this is the Y term. So we know it's going to be log K equals something times 1 over T, which is the X term, plus the Y-intercept, which is 3, right? Here's the Y-intercept. But what is this term in here? That term happens to be delta H0 over R. So that's the slope of this line, delta H0 over R. And this one here is equal to delta S0 divided by R. All right? So we really don't need to know that one because the question is, what's delta S? So we just set that equal to 3. Okay? So what we really need is, what's R? R is 8.314, isn't it? 3145. 3 times 8.3145 equals about 25 joules per kmol. So we found out what delta S was just by reading the graph and knowing what each of these terms stands for. Okay? Now, if we wanted to know what K was, how do we get K? Well, the y-intercept is 3. And the y-intercept here, 3, is equal to log K, right? So we would take the anti-log of 3, that gives us K. But that wasn't the question, just in case it was. Okay. I don't know if we can see. Yeah, we can see that one. Red shows up better than green. Okay. How about, let's see if that was in there. How about this one? This one doesn't have a number either. Suppose we're given this information. Okay, delta H in this column, delta S in this one, and delta G in this one. So these are all positives, and then I'll give you the reaction that this pertains to. Okay, so when a stable diatomic molecule spontaneously forms from its atoms. So what does that mean? A diatomic molecule spontaneously forms from its atoms. Okay, that's spontaneous. That's where I'd start. If it says spontaneous, that means delta G is what? Negative. So it's either got to be this one or this one. So you can throw out A, C, and D. Now we just have to decide, is it this one or that one? So let's look at is this one more ordered or less ordered than that one? If we're going from 2 moles of this one to 1 of that one, it's more ordered, right? So delta S is negative if we're going from 2 to 1. Okay? So where's delta S negative? Well, it turns out both of them are, right? So now we have to find out which one has a different enthalpy, which one's positive, which one's negative, what case. So is this one going to be higher in energy or lower in energy than this one? Think about it in reverse. Remember when we were talking about, well, maybe that was last semester. Maybe it was this one, I can't remember. What does it take to break that bond between two atoms? You have to put energy into it, don't you? Right? So the delta H in this direction is negative, but positive in that direction. Ooh. Delta H. If X2 is lower in energy than this one's lower in energy, this one minus that one would give you a negative. So it's actually the other way around, right? This is more stable than that one, so it's lower energy. So this one has there, and this one has there. So it's make that one 2 and this is 1. So the energy change is this one minus that one. And if this one is smaller than that one, that makes the overall negative. So E has to be the answer. It's not intuitive. I'll give you that much. You have to know what the energies are. And reactions generally when they run downhill, right? That's the way they want to go. They want to go downhill in energy. This side has lower energy than that one. So this one minus that one gives you a negative. Actually, the delta H was the hardest one to deal with. The other two were simple. Okay, let's see. I think we got one in here. Look for one that says KP. K in terms of pressure. Okay. Number 59. Okay, for a certain process at 300 K, and it's the temperature, the delta G is negative 10.4 kilojoules. The delta H is negative 7 kilojoules. If the process is carried out reversibly, what does that mean? That means we run this reaction so that it's right on the knife edge of going one way or the other. So that means on a microscopic scale, it is reversible. So we carry it out reversibly. The amount of useful work that can be performed. Okay, so when we say the reaction is reversible, we carry it out reversibly, that means delta G is the maximum energy available. Okay? If we don't carry it out reversibly, then we'll never make it to that much energy. We can't get that much out. Right? It's only when we carry it out reversibly that we can get the maximum energy out. And even then we can't, but theoretically speaking. So the amount of useful work that can be performed is what? This is the key. If you carry that reaction out reversibly, then you're saying this is the maximum amount of work, minus 10.4 kilojoules. That's why the answer for 59 is D. If we don't carry it out reversibly, then you would need something less than 10.4, actually, mathematically speaking, greater than, right? Because you'd need a number that's, the absolute value is smaller than that. So you would need 9876 to get that much energy out. Okay? That was kind of a thought problem there. Let's see. Okay. 60 and 61 kind of go together. 60 is looking for delta G. 61 is looking for delta S. And it's easy to calculate delta H from that reaction, because you're given, well, you're given both delta S's and delta H's. Right. So all you need is the balanced equation. So let's do that one. This will give us practice balancing equations again, because it is a perishable skill. What movie was that? Where did I get that statement? Reacher. John Reacher. Remember that movie?
I don't think I've ever seen it.
Oh, you haven't? Oh, you got it. It's good. It's a Tom Cruise movie. He was talking about sniping. It's a perishable skill. Okay. So we're given these values of delta H formation and delta S, S for each of these components. But in order to use them, we need a balanced equation. So when ignited, solid ammonium dichromate, and dichromate is a, I think it's a 2- charge. Let's see. Pretty sure it is. Yep. So that's 2-. That means we need 2 of these. Solid. Decomposes. And the decomposition produces nitrogen gas. And water vapor. That's a gas. And chromium-3 oxide. Chromium-3 oxide. So that's 2-, that's 3+. We need 2 here and 3 there. I think. No. Wait a minute. mistake. There we go. There we go, 3. Okay, this is a solid. Okay, so we need to balance that equation. I don't know about you, but that's not one I want to tackle in my head. So, do we have ammonium on both sides? Nope. So we're going to have to take nitrogen out of there. Chromium, hydrogen, chromium, and oxygen. So we've got 2 nitrogens, we've got 8 hydrogens, 2 chromiums, 7 oxygens. On this side, we have 2 nitrogens, we have 2 hydrogens, we have 2 chromium, and we have oxygen. 1, 2, 3, 4. There we go. Okay. So nitrogen's okay. Let's go to hydrogen and see. We're going to leave the nitrogen alone. Of course, might as well because it's the same on both sides. So we want to make 8 hydrogens. We've only got hydrogen here, so we've got 4 there, which makes 8 here, and it changes the oxygens. 4 and 3 is 7, right? All right. That's it. We're balanced. We just needed 4 waters. The whole thing's balanced. Okay, now what do? You got to get that balanced equation before you can calculate these other values. We're looking for, how do you get delta H out of this? Well, if we know the enthalpy of formation of each one of these and that one, we just take those and subtract this one. So the delta H for this one is 0. And this one is 4 times water, which is 0.118, oops, sorry, that's entropy, minus 242. And then chromium dioxide is 1 times minus 1147. And these are in kilojoules. And subtract this one. We only got one of them. So we have a minus 22.5. Right. So when we do the math, we get minus 2.093 times 10 to the third joules or kilojoules. That's kilojoules. Let me do the math to be sure. 242 times 4. 1147 plus, and then plus 22.5. That's, do my math wrong? 242, 747, 2.5. Let's do it one more time. 242 times 4. Change the sign because it's negative now. And then 1147. Okay. And then plus 22.5. There we go. 2093 times 10 to the third kilojoules. Okay. That's delta H. Okay. We can do delta G next. So into delta G, no, we can't. Can't do delta G next. We need delta S first. Why do I need delta S first? Because delta G is equal to delta H minus T delta S. So we got to have delta S first. So delta S for N2 is 0.1915 kilojoules per mole. Okay. Plus 4 times water, 0.1187. And then chromium dioxide is 1. So that's 0.08118 minus this one, which is 0.1137. Okay, just looking at these, what does this tell you about the state of the entropy, the intrinsic value of entropy for each one of these? The lowest one is this one, which relates to chromium 3 oxide. So what does that mean? That means this is probably a more ordered crystal structure for that one than for any of the others. That make sense? This one has the most ordered crystal structure of any of the others because its standard entropy is lower than anybody else. Okay, so when we get that one calculated, we should have a value of 0.6338 kilojoules per mole. Okay. Now we can calculate delta G. So we have negative 2.093 times 10 to the third minus, what's the temperature? Oops. What's the temperature? Standard temperature. 25, so that's 298 K times this value, 0.6338. And that should give us 2281. Let's see. Negative actually. 9 kilojoules per mole. So 60 and 70. 60 asks for delta G. So this is number 60 answer. And that's B. And then 61 asks for delta S. This one. It's a 61. And it's D. Okay. So that's why I did them both together, because they're based on the same reaction and the same basic information, just asking 2 different questions. But in order to get the answers, we had to calculate this one and that one before we could get this one. We're doing on time. Ooh, no, coming up on 20 minutes before lab. I'm trying not to leave anything out that you might need to do well on the exam. About, let's see, where is this one? About this one, 56. There we go. Yeah, we can take a break.
I was gonna say, you keep on going.
That's all right. We'll take just a short break. So let me pause this and then, here we go. Okay. Let's see, where was I going? Oh, 56. So this system is equilibrium at 25 degrees. PCl3 gas plus chlorine gas. If we're going to say equilibrium, it has to be that. PCl5 gas. And the delta H equals negative 92.5 kilojoules. If the temperature of the system is raised, right, if we increase the temperature, what happens to the ratio of these partial pressures, PCl5 to the pressure of PCl3? Right? Does it increase, decrease, stay the same, or is it impossible to tell? Okay. Let's see, the equation is balanced, and that's good. All we can tell right off the bat is this is exothermic. That may mean something and it may not. Let's look at it first. Before we go to this right here, let's look at it this way. We may not need to be to use any of the information in this chapter, actually, right? What do we know about that reaction? If it's exothermic, which side is the heat going to be? Is it going to be as a reactant or product? If it's exothermic, heat is a product, right? So that heat is on that side. Now, what happens when you raise the temperature? You're adding heat, right? So you're adding this one, and it goes back that direction, right? So that decreases PCl5 and increases this one. So this ratio decreases based upon Le Chatelier. Okay, so I guess you could consider that a trick question. In the chapter on entropy, stick one of these in there. You really don't need to know anything about the entropy to answer this question. Le Chatelier answers it for you. Okay. Let's see. Kind of winding down here. How about, let's see, hold on a second, let me find it. I'd like to do this one. It's in here. If it's not, I'll have to do it without a number. Okay. Looks like yank here. In this version, anyway. I bet it's in the other version. Okay. Well, let's do this one without a number. And you'll probably find one just like it in version 2 of the document. So let's see if I got enough juice left in this marker to get this one done. Okay, suppose we have this reaction. Okay, and the delta H for this one is negative 56.8 kilojoules, and the delta S for that system is negative 175 joules per K. And our temperature is 298 K, which is 25 degrees centigrade standard temperature. So we mix them together, and they start off with their partial pressures of this one. No, let's see. In containers, is it? This one has a partial pressure of 2.4 atmospheres, and this one has a partial pressure of 0.42 atmospheres. You know what? The choices that were given, N2O4 will decompose into NO2, or NO2 will dimerize into N2O4, or the system is at equilibrium, or the total pressure must be known to answer this question. All right. We know what the total pressure is to start with, right? Because Dalton's law says the pressure to start with is just the sum of those two. So it's 2.82 atmospheres. So that's not an issue. But is the system at equilibrium? That's the question. How do we know if the system's at equilibrium? Well, we have to know the K. And we have to compare the Q to the K to know if it's at equilibrium. How do we determine the K? Well, we've got K in this term. See, let me put it over here. Equals negative RT log K. Okay, so we can find out what the K is here if we know the temperature, if we know what delta G is. Right? But can we tell delta G from this one? Well, actually, yes. You can, because you've got the delta H and the delta S. You can tell what delta G is. Delta H minus T delta S. Right? So we can find out what the delta G is and then use it to find out what the K is. And then calculate Q. So what's K? The expression for K is just the partial pressure of N2O4 divided by the partial pressure of NO2 squared. Okay, so we could use that to calculate the Q here and then compare it to the K that we get from here. So if this is negative 56.8 times 10 to the third, let's go the other way. Because we want delta G in kilojoules. So let's do this one as minus 56.8 kilojoules, and then minus a minus 0.175 kilojoules per K. Oh, we need T times that, 298. There we go. So that's delta G. Calculator. Does everybody follow me so far? Okay. 6.8, same sign. And this one is 0.175, 298 times, and a negative negative, so it's going to be plus. Okay, so I get negative 4.65 kilojoules for the delta G. So now we can put that in here. Negative 4.65 kilojoules equals negative R, which is 8.3145. T is 298. And then log of K. So now we can find out what K is. We just have to take this one divided by that one divided by that one. So it's 8.3145, change that, divide, and then 298 divide. So log K equals 1.867. Oh, sorry, I'm reading that wrong. Dyslexic. 8767 times 10 to the minus 3. Okay, and then the anti-log of that, the anti-natural log of that is e to this number. So I just punch in that one, and that equals 1.002. It's K. Okay. I did something wrong, I think. Yeah, I did, some calculation was wrong. Let me see if I put these in here right. Delta H minus 56.8 minus a T times delta S in kilojoules. That's joules. This is kilojoules. Okay, so I need to check to make sure that one's right. Okay. That's a negative. That's a negative. Okay, we're good so far. 298 times, and then 56.8. Oop, that's where I made the mistake. One 1.0895 times 10 to the second kilojoules. Here we go. 1.0895 times 10 to the second kilojoules. Now we divide that by 8.3145, change that, divide, 298 divide. So this is negative 4.397 times 10 to the minus 2. Now I take the anti-log of that. So that leaves me 0.957. K. I'm still getting a weird number. See if I did this right again. This one is 52.15 joules. This is 56, so it should be a negative number because it's a negative negative, right? So 56.8 plus, went the wrong direction. That's a negative. I did that wrong again. Can't win for losing. Let me try it one more time. 0.175, 298. It's going to be a positive, and then a 56.8, that's a negative. All right, 4.65 kilojoules. Oh, let's hope you don't have this much trouble on the test. Okay. Now this one times that one. Is that the right value for R? Yeah, 3145. And 298 times negative divide 1.876 times 10 to the minus 3, and then e to that number. I'm still getting 1.002. All right, let's go with it. See what we get. If this is K, then this K is equal to 1.002. So what's the Q? The Q would be this one divided by this one squared. Okay? 0.42. And I get 13.6. Okay, what does that mean? Well, if you don't have the relationship memorized, if Q is bigger than K, which direction is it going? Back that way, right? So if Q is 13.6, that means we've got too much of this, not enough of that, because it's supposed to be 1, right? So we've got more of this than we need, and Le Chatelier is going to run it back that way. Now, what does that mean to the question? N2O4 will be decomposed. Right, it's going this way, which, well, that's the answer. We're going to decompose N2O4 based on that relationship compared to this one. Now, we could have taken a guess. You know, this is huge, this is small, right? But if you have to show your work, that's it. All right. Not sure how this one got messed up. Yeah, I do. I need to check my calculations. Fortunately, my mistake here doesn't change the answer. Okay. We're past 4 o'clock. Does anybody have anything else that is burning a hole in your brain? Because my markers are about dead. Oh, we lost everybody. I guess they got tired.
I'm still here. Can you not see me?
No, I can't see you.
I'm here.
Okay. Let's see. Let me look down here. Manage participants. Oh,
It
I
looks
see you
like
on here. I just didn't see your little inset. But your participant, yeah, you're still there.
Yeah, I'm still here.
Okay. I think I've about exhausted myself. My advice is to go to the version 2. Take a look at the version 2 as well as the version 1. If you've got time. And look to see, you know what I would do? I would take version 1 and version 2 and just skim through version 1 and then skim through version 2. And if you do it quickly enough, you can remember seeing this type of problem in 1. And if you don't see that one in 2, look at those particular ones in 2. And that'll cover all of your bases. Otherwise, I'll see you after the break, Thanksgiving break next week. And we'll do this battery lab. We'll have to get, well, let me see. You check it, sure. I won't tell you wrong.
So the next exam is on December 2nd. I'm gonna write all the dates down.
Yes, December 2nd. And then
what's the next lab
we'll jump into electrochemistry.
on December 2nd.
Yeah, right after the lecture, we'll do electrochemistry. Do that so that when we go in the lab, it'll make sense.
Right.
And then
And
the lab, right. And then the last exam will be on the 9th. And that's when your electrochemistry report is due. And there's no formal report on the battery lab. You just answer the questions that are in the hard copy and turn it back in. So you could probably do that on the same day.
Okay. You're talking about this new one, right?
Yes, that one. Okay.
And
Question?
I'm just trying to make sure I got all my dates right. You know what I mean?
Okay.
So the 25th, no school.
Right. That's right. 18 plus 7 is 25. Yep. Okay. We'll see you in a couple of weeks.
Well, so we only have 2 more tests.
Now let me see. I need to ask, did I get your
I
KA?
actually forgot to turn it in. I'm going to turn it in.
The KA?
Yeah, I just
Okay.
turned it in. It should be in Dropbox.
Okay. And then the other one we've got to do is on the 2nd is the formation constant lab. Right. So you can get that one done over the holidays. I think that's it. You got any questions, Julianne?
Mm-mm.
Okay, we're done for today.
All right.
See you in a couple of weeks.
All right. Happy Thanksgiving.
You too.